ARPA-E moonshots in energy storage? Can a few
Yes, we
people say
can.
yes?
Yes.
Yes.
Goodness me. I apologize for keeping you all waiting. Okay, I've introduced myself. Let me introduce ARPA-E for the few people who don't know us. We've been around for 15 years. We were stood up by George Bush and then funded under Obama. We've enjoyed good bipartisan support in our 15 years. And during that time, we've funded 87 programs comprising about 1,700 individual awards. And we get about $500 million a year of your money to fund early stage R&D. I'm going to talk for about 20, 25 minutes, and then we'll have some questions, hopefully, if there's still some time. But I encourage all of you to connect with me on LinkedIn, and so we can talk further as you determine. We've done over the years 9 very specific programs relating to batteries. So the top 6 that you see here are ones which are really done now, closed up. And the ones at the bottom, the 3 you see, EVs for All, Propel 1K, Circularity, I'm going to talk a bit about today. Those are active programs. So we have teams running projects related to those topics, and we'll explain what those topics are. We're always working on the next program. So I have a colleague who's working on something. Not allowed to talk about that, but there may be a future program coming. I guess this is our sort of badges, our, hey, what have we done that you might know about? So these names on this list, you'll know some of them, I hope, are companies who we funded. Many of them we funded in their early days. So we could claim they possibly wouldn't exist without our early stage funding. And these are the ones who are surviving. So I could have put more names up here of people who didn't make it. And of course, there's lots of universities we funded too, and large companies, and they're not on this list. But hopefully you know some of these lists. This is our credibility, if you like. We take risks. We look for transformational ideas, but we're willing to see as much as 90% failure rate as we invest in these early stage opportunities. You all know about battery problems, right? Whether it's us as people or whether it's companies, we're all trying to solve problems, and batteries tend to have all of these problems. And so our programs are typically trying to solve one or more of these at a time within a specific energy application. Now, just to do a quick check, everybody seeing this chart that says energy storage problems and challenges?
Yes.
Beautiful.
Yep.
Good.
You're good.
Now, we focus on problems. So unlike other agencies who fund roadmaps, hey, we're going to go and invest in sodium, or we're going to go invest in lithium sulfur, we always start with the problem. What problem are we trying to solve? And it's the process of framing that problem, determining metrics that would really help understand what is needed to solve that problem, and then inviting applications to solve the problem. That's our process. And we try and maintain a certain agnostic perspective about which technologies we're going to fund. The first program I just want to illustrate that is a program called DAYS, right? This program was initiated back in 2017. And at that time, hey, we all knew that solar and wind were wonderful, but the issues with them are intermittent and they're not always close to where we need the energy. And so it was recognized that we need affordable energy storage. And we captured a metric as in terms of levelized cost of energy storage, as if we could achieve that target for energy storage, 5 cents per kilowatt hour, that would represent getting close to a solution for this particular problem. So that was put out there as the metric, along with, hey, we're looking for things between 10 and 100 hours. And we had a whole series of applications, and coming out of that, there were 15 teams that we funded in these 5 general technology themes. So you can see electrochemical is one of the themes, but there were other themes as well. So we funded 15 teams, the ones we thought were best. I think there was like 6 that were in the battery section. The 2 that have been the most successful so far in terms of teams that are doing now significant commercial demonstration aren't battery companies at all. One is a geomechanical. They pump water down into the ground, a sort of pumped hydro in reverse. And the other one is Antora, who heat up a carbon block to 2000 degrees and can either dispatch that as heat or can dispatch it as electricity via thermophotovoltaic cells. So a good illustration of an ARPA-E program: frame a problem, set some metrics, invite applications, be technology agnostic with the ones that we choose. And I hope, as a battery person, that maybe some of the electrochemical storage things come through ultimately, but at the moment they tend to be lagging some of the other technologies. Here's another one. This is called EVs for All, and it means what it says. This program was initiated during COVID. And so we have made the simple observation that everybody wants a smartphone. Not everybody wanted to wear masks or get vaccinated. And we looked at EVs and said, if we're not careful, EVs will become similar. Some people will want them, but lots of people won't. Maybe some people will either consider them a curse from the government, heaven forbid. And so we focused on detractors. So we said, well, what are the reasons people won't want EVs? Well, if you have a home with a garage, there's nothing more convenient than an EV. If you don't have a home with a garage, charging is going to be pretty inconvenient if you have one. And 37% of the people who in America do not have homes with garages or carports. So we said we need to get to really fast charging to take that away as a problem. If you live in California, Texas, or Florida, hey, you don't have to worry about severe winters. But if you live in Minnesota, Wisconsin, that's a different matter. Car can lose half its range in the winter. So we wanted to address that. And finally, affordable range. Yes, that's about the cost of new batteries, but it's also the cost of used batteries. And a lot of that comes down to how much capacity are you using as you cycle the battery. So we wanted to tackle that too. So here were the metrics for that. We had 2 tracks on this one, and you'll immediately recognize the 2 tracks that we were targeting: 200 watt-hours per kilogram. This is at the cell level. So this is really chemistry of the cell. And that's about where LFP was coming in. So when this program was put out there, LFP was just coming in as, hey, hang on a minute. LFP can be a good EV chemistry. And so the 200 watt-hours per kilogram was set based on that. The 400 watt-hours per kilogram was based on what we thought we know was coming down the road. So, you know, silicon anodes, solid state maybe, lithium sulfur, higher energy density for more range, and or bigger vehicles. And you can see we had a 5-minute charging metric for the 200 watt-hour per kilogram and the 15-minute charging for the 400 watt-hour per kilogram. That's 80% capacity input. And you can see there, we wanted to cut the energy loss at -20 from 50% down to 15 to 20%. We had a new cell cost at $60 per kilowatt hour. We thought that was pretty aggressive at the time, but as we all know, I think that's where LFP is now. So maybe not so aggressive. And finally, we wanted to decrease the capacity loss. So many of you know that, hey, we judge capacity loss maybe after 1,000 cycles down to 80% capacity. And we said, well, if we can improve that to 90% of capacity, then that's a 2x improvement. Here are the teams that got funded out of that. So this is $42 million in total. The ones on the left, and maybe this isn't so surprising, they're all lithium-ion liquid or liquid-based solutions. We have 2 anode oxides, Ti-Fast and Ohio State. South 8, which is a pressurized electrolyte, and Virginia Tech doing some things I can't tell you about. And then Project K, which you might guess immediately, that's about potassium. That's a potassium-ion battery. So they're all the 200 watt-hour per kilogram trying to get to 5-minute charging and actually doing very well, I can tell you. And on the right-hand side, far right-hand side, you have the hybrid solid state and the pure solid state. So you've got Ampere there and Solid Power, who are sulfide, 100% solid state. You have 24M, which is actually a sodium metal hybrid solid state solution. And then the University of Maryland, which is a lithium LLZO type of solution. And they're the ones who developed the baseline technology for ion storage systems, who I'm sure you know. Now, we all know that over its history, lithium ion has had a colorful history as far as safety is concerned. So we wanted to make sure with these new chemistries that we were looking after safety. And so 2 extra teams were commissioned, one led by Sandia National Labs that includes UL, Purdue, and another university, and then NREL, which includes Exponent and UT Austin. So those 2 teams are working with these 10 teams to develop safety protocols for these new chemistries. This is a program that literally was only announced 2 weeks ago in terms of the awardees. You know, we've been sort of, I would say brainwashed, but we've got ourselves into believing that recycling is the way we're going to do everything, right? And that's about taking a battery when we determine it's at the end of its useful life, and we're going to take it back to almost its raw elements. But when we do that, we're going to take a lot of energy to do that and create a new battery. But also we destroy a lot of the value that we created when we made the cells, when we made the batteries, when we made the battery management systems. So far better if we could remanufacture, repair, or regenerate to capture that value and reduce the amount of energy required. So that was the theme here, and we had 3 categories, performing categories. How do we extend the life of batteries? How do we make disassembling batteries easier? And then finally, how do we monitor batteries better so we can take out maybe a few cells that are failing early so that the rest of the battery can continue. Category D is about life cycle analysis, and then here were the metrics. So if you look at that top metric as an example, 1,000 kilowatt hours per kilogram. Well, that's like an LFP battery. That's 200 watt hours per kilogram that you cycle 5,000 times. And you run the numbers, and that's equivalent to about 1 million miles. Now, demonstrating that a single cell can do the equivalent of that is not so difficult. Demonstrating that you can do it in a battery pack is a different matter, and that's one of the things that this program is about. And so this was announced either last week or the week before. 13 projects coming out of this. Iontra, Onto Technology, Purdue, Sea Lion Energy, University of Colorado, St. Gobain, BMW, University of Michigan, UC San Diego, Toyota, Sonocharge, and High T Tech. So you can probably find those if you go onto the ARPA-E website. Okay. So that's a quick view of a few programs. The next one I want to dive into a little bit deeply. Can everybody still hear me okay?
Yes.
Yep, you're good.
Hopefully I'm going to talk for another 10 minutes and then we can have some questions. This is a program which is called Propel 1K. And we started work on this almost 3 years ago now. And it was launched in July of this year. So it took a long time to put together. And we said, okay, well, EVs, we've got EVs, right? But what about heavy duty electrification? So we did this analysis. You can see it on the chart here. If we take today's batteries, let's say they're 200 watt hours per kilogram at the battery level, and we stick them on a plane, 100-seater plane, we can do about 150 nautical miles before we have to start throwing people off the plane. 500 watt hours per kilogram, which is maybe where we're going in the next 5-10 years, gets us a little bit more, but not maybe enough for us to seriously consider batteries powering regional jets or regional aircraft, one should say. It's only when you get to 1,000 watt hours per kilogram that you get to something that you could seriously consider for regional flight. So we talked to people about this, and I'm sure there's some of you on the call who think we're crazy, and some of the people we talked to thought we were crazy. But we were surprised a lot of people thought there might be a way to do this. And of course, a lot more people who thought that if we could do this, it would be very impactful. So not only would it allow for regional aviation missions, but you could electrify all US railroads. You could electrify all maritime operating in US territorial waters, so barges, tugs, ferries. Also something called Jones Act freight, which is the freighters and small container ships that go from US port to US port. And finally, you could go for long distance trucks, so 500,000 miles without having to recharge. Let's remind ourselves why electric is compelling, right? We've lived with ICE for a long time, but there's a lot of reasons why electric will be compelling if you can do it. Energy efficiency, a lot of the energy infrastructure is in place. reduce noise pollution and zero emissions, of course, cleaner air, CO2 reductions. But also when you can do something like this, it allows you to consider new business platforms and operations. And I'll point you to the picture on the right, the middle picture. That's the Yara Birkeland, which is a Norwegian container ship that goes up and down the fjords, still going through its, I guess, proving tests. I think it takes about 100 containers. It can do about 40 miles, I believe, and it can be totally autonomous. So you can start really considering different business models if you have a different way of doing things. You know, if you have an electric aviation system, you can fly very close into cities if you have short runways, because they're going to be quiet. So how do you do this? How do you go about even thinking about something like this? And I actually jotted this down just before we met today because I wanted to, well, you have to think a little bit differently. You have to appreciate that you're working with big, and I'll explain that in a minute. You have to think about anode materials differently maybe than the way we typically do. You have to innovate the heck out of packaging. I'm not sure if heck is a technical word, but it's in this presentation. And then you have to sort of appreciate what is different. So one of the things different about these applications is you need to change over very quickly. You can't have long charge time. So that has to factor into your thinking. But also because you're using this thing all the time, plane, train, whatever it is, you know, self-discharge becomes a lot less important. You don't have to worry about self-discharge maybe so much. So here's some examples of, you know, that thinking. Here's a chart. So you've got motive power on the vertical and energy along the bottom. And so this is really where we're playing today. And these are both log scales, by the way. So this is state of the art. We've got passenger EVs with what we have. You know, Class 8 truck. Yeah, you can have a Class 8 truck that does 250 miles, but if you wanted to do 500 miles, you have to give up about 20% of your load. So you need more than what we have today if you really want to do long distance Class 8 trucks. Then we have all the other applications. So we targeted this. This is the sort of area that we're targeting with this program that we're calling Propel 1K. And so the 1K stands for 1,000 watt-hours per kilogram. So you're starting big, right? And that's important. If you know you're going to be big, then you can configure your chemistry to lean into big. Metals, right? Electroactive fuels. The jet energy of jet fuel is 12 kilowatt hour per kilogram. Lithium is just shy of that. Aluminum, magnesium are pretty respectable. Even if you have to carry the oxidized version on board, you're still talking a lot more than 1K, and you're talking a lot more than the 0.2, 0.3K that we have today. So one of the things we have to do is think about packaging, right? This is how we package something that we're putting into a 40-foot container today. We package it 7 times. You can see it on this chart here from the active material packaging on the far left all the way through to now I've got to install batteries into some kind of container. So the question, right, we're not here to invent, we're here to inspire. How can you go from 7 packaging steps maybe down to 4 or 5 and take out weight, take out volume? Here's another way of looking at that. So our goal in this program isn't 1,000 watt-hours per kilogram at the cell level. It's at the system level and its end of life. So if you look at this chart here, this explains why. If I have a cell that delivers 1,000 watt-hours per kilogram, that's great. But then I'm going to have to pack it. Oh, by the way, don't use that cell over 95% or below 5%. Oh, by the way, I didn't tell you, did I, that it's going to lose 20% of its life over its time capacity over its life. So, you know, when we talk about what we're trying to achieve here, this is really where the 1,000 watt-hours per kilogram needs to be if we're talking about aviation. So if you have to deal with all those factors that we've just looked at, then we actually have to have cells that can deliver 2 kilowatt-hours per kilogram. So we need innovation here, right? Innovation, packaging, innovation, how much of the state of charge can I use, and with cell aging. Now, we don't just sit in an office in DC and come up with these ideas. We spend a lot of time talking to a lot of people. And as part of that process, we do have a workshop. And so we had a workshop probably 6 months before this program was put out on the street. And we had all these organizations come. So you can see here a whole different mix of organizations, everybody from people who understand the applications, Lockheed Martin, Toyota, to people who develop solutions, people like Lytton, Microfast, Form Energy. So it's working with this group that we were able to come up with metrics, and working with this group to make us believe that this was worth a shot. So we had 20 teams, 20 groups who presented at this meeting that said, we think we have something. And that encourages us to move forward with a program. And that program, these are the key metrics for the program. So you can see the 1,000 watt-hours per kilogram that I mentioned. See other metrics here. You can see we took 2 tracks. There's an aviation track, which involves more power because you need more power to take off. And there's a railways and maritime track that needs less power, but the cost base is lower. The levelized cost is based on jet fuel. So that 30 cents for aviation is jet fuel. The 20 cents under railways and maritime is the cheaper fuel oil that's used for ships and boats. Safety, we didn't neglect, right? If you're going to put a battery on a plane, you can't have thermal runaway. You can't have a sequence like we've all come to accept for lithium ion, where one thing leads to another, leads to another, leads to another, and then you have thermal runaway. You have to have a chemistry that's not going to do that. Yes, you're putting a lot of energy into a box. Yes, that has to be managed, but you can't afford to be sitting on a plane knowing that you haven't got time to go out should it go into this kind of sequence. I'm going to try and close this within the next 5 minutes. We gave people strategies, mechanically rechargeable, a swappable energy box so you don't have to charge in the application, separating power and energy. You need something a lot more than a flow battery, low energy, but maybe you can pump electroactive slurries of anode materials. This is Michael Phelps. When he breathes in 2 breaths, he breathes in 20 liters of air, and there's enough oxygen in that to power my cell phone, as the lithium-ion battery does in it today. Gantrify, that's about combining electrochemical function with mechanical structure. Revisiting the past, that's the great thing about batteries. People ask me, why are you still in batteries? Well, because technologies appear today that help us solve problems we couldn't solve yesterday so that we can be successful in the future. So one of the ideas, for example, was rechargeable lithium CFX. Lithium CFX is a high energy density primary battery. If you can make it rechargeable, then you can do some very interesting things with it. Forget temperature as a constraint. Well, obviously it is a constraint, but don't think room temperature, think higher temperatures. So, hey, we do put jet engines on planes that run as high as 1,500 degrees C. We shouldn't inherently be scared of having high temperature batteries. And then finally, we didn't want to forget our fuel cell brethren, but we didn't want to just do liquid hydrogen and pressurized hydrogen. We wanted to do maybe a packaged hydrogen that would be a lot safer and easy to process in these applications. So I showed you the teams earlier for EVs for All. That's the lead team I showed you. An ARPA-E program typically has a team of a number of organizations. So we funded this one, 13 teams we funded out of this. And so each of these, category A was the aviation one, you may remember. So University of Illinois, Chicago is the lead team, Argonne and the University of Nebraska team members. Illinois Institute of Technology is the lead team, Argonne and Raytheon or RTX are team members, and so on. We thought this was so out there in terms of an idea, we didn't fund it as we normally do. So we've actually funding this program in 2 phases. So basically we're giving people between $900 and $1.5 million for an 18-month program. Just show us you have something. Show us some chemistry. Show us some chemistry that would help us believe that trying to do this 1K has merit. Now, I can't tell you who proposed what for obvious reasons, but I can show you where the range is, right? So this is the kilowatt hour per liter versus the kilowatt hour per kilogram map. So there's 13 dots that you can see here, which I've I've ringed in the dotted green circle. That's what people proposed for the chemistry only. And so that's what they have to show us in the first phase of this program. 2 of them can't do that. So they actually propose system numbers. But you can see there's people who believe they could do this. And we like a diverse portfolio when we do a program. So we have some solid state lithium air in the mix. We have some packaged hydrogen. We have 2 rechargeable lithium CFX projects. We have a couple of molten sodium, and we have 2 aluminum projects. And what I'm going to suggest here, because I know we got started late, is I included a bit of information here for 3 of the teams, which you can go and look at. In the left-hand corner, the bottom left-hand corner of this chart, it says Propel 1K kickoff meeting. If you type into your browser at some point, Propel 1K kickoff ARPA-E, it will bring up this kickoff meeting, and you can scroll through the agenda of that meeting, and most of the presentations that the teams presented, you can find there. So you can browse certainly 7 or 8 of them and see what they were saying. And there's no reason why you shouldn't reach out to them and find out in more detail, as much as they will tell you what they're doing, why they believe they will be successful, and maybe some of the challenges that they have that you might be able to help with. So this is a very risky program. We know if we have one team that succeeds, then it will be worth the effort. And we're very excited to give us all the opportunity maybe to do something in batteries that would be exciting for the future. So I'm going to stop sharing so I can see you all. And I'll then willingly ask any questions anybody has.